This lecture is going to be on the topic of graph isomorphism. At a high level, we want to know whether two graphs are the same or not, because it can actually be pretty tricky. These two graphs, for example, are identical, but by shuffling around the way they're displayed, it's not obvious that they are identical. And if you recall, when we represent a graph as an adjacency matrix, for example, we're assigning an arbitrary ordering to those nodes. And this can make it difficult to tell whether two adjacency matrices are actually representing the same graph, because there's many different ways that you can shuffle up an adjacency matrix, especially as the number of rows and columns is large. Why does this matter? Well, one reason it matters is that it gives us a tool for analyzing the representational power of GNNs. You can ask questions like, if G1 and G2 are isomorphic, if they're the same graph, does your GNN give the same output? I think that's a desirable trait of your model, that if you give it the exact same graph, you'd probably want the same output, even if you shuffled up the ordering. But also, if G1 and G2 are not isomorphic, does your GNN give different outputs? If your GNN gave the same output for every graph, even if they were totally different, that would obviously be a bad thing. So you're going to need to balance these two forces. If you recall from our permutation symmetries lecture, we introduced this notion of a permutation matrix, which essentially shuffles the order of rows. And we can formally define the isomorphism of graphs if you say that essentially there is a permutation matrix that if you shuffle up the adjacency matrix of one graph and you get the adjacency matrix of another graph, then they're isomorphic. And then you have to be able to shuffle the features and get the same thing. But this basically just means that if you can shuffle the ordering of your representation of a graph and recover the other graph, then they're isomorphic. Now you might think the brute force approach could be that you just test every permutation matrix until you find one, or you've exhausted all of them and seen that they're not isomorphic. But the number of permutation scales is the factorial of the number of elements. And for only a small number of nodes, like 100, we're already at 10 to the 157th power number of possible permutations. So we're going to need a different approach here. This brings us to the Weisweiler-Lehmann algorithm, and I apologize for the pronunciation. It's actually a family of algorithms that test whether two graphs are isomorphic or not. And the steps are as follows. And I'll go into a particular example that'll make it a lot more clear, because at the abstract, this seems a little bit complicated. It's actually quite simple. So the first step is we're going to assign an initial label to each node. And then we're going to iteratively map new labels. And the way that we do that is for each node, we construct a tuple. The first element of the tuple is the current label of the node. And the second element is a multiset of all of the neighbors' node labels. And for each unique tuple we get by doing this for every node, we create a new color and assign that to each node. And then we partition the graph into node subsets based on if they share the same color or not. And then we continue this process of remapping to new colors and partitioning based on shared colors until the partition stops changing, so that essentially the same nodes are grouped together and share the color consistently from iteration to iteration. The main idea here is that we're going to assign a label to each node that encodes the local information. For example, a color might represent that this node is connected to one node of degree 2 and one node of degree 3. And all of the nodes that share that property will have the same color. And then when we have two graphs, we can collect the labels and compare their distributions and see, okay, if they have the same counts of all of these colors, then they're isomorphic. Let's look at an example. We first start out by assigning every node the same label. Here is 0, represented by blue. Now we create the tuples for each node. Recall that the first element of the tuple is the current label. So each of these tuples, the first element is 0 because they all have the same color. And then the second element of the tuple is all of its connected neighbors' current labels. So this one is connected to 3 nodes, so it has 0, 0, 0. However, this is only connected to 2 nodes and has 0, 0. This one has 3, this one has 2. What you see is that this multiset essentially encodes the degree of each node at this first iteration. Every node that has degree 2 has the same tuple here, and the 2 nodes that have degree 3 have the same tuple. What we end up doing is assigning a unique color to each unique tuple. In this case, we just pick that this one's going to be called 1 and this one's going to be called 2, and then recolor our graph using this scheme. Now we have 4 nodes with this color and 2 nodes with that color. Finally, we can partition the graph based on shared colors. So all of the nodes that have the orange color are B, D, E, and F, and the nodes sharing this color are A and C. We can repeat this again. The current label for this node is 2, its neighbors are 1, 1, 1, and that's the same for this node here. This node's current label is 1, and its neighbors are 1 and 2, and that's the same here. However, this node, it's also currently a 1, but its neighbors are 2 and 2. Whereas this node has neighbors 1 and 2, this node has neighbors 2 and 2. That means they will get, since they have different tuples, they will get different colors in this iteration. These 2 nodes now have this yellow color because they have 1 and 2, and this has a different color, which we've now chosen to be green. Whereas before we had 2 unique colors, now we have 3 unique colors. And the partition we get from this is EF, BD, and AC. We can do this one more time, which will go a little quicker. We collect the tuples again. We end up getting 3 new colors because there's 3 new unique items here. We're calling them 6, 7, and 8. Using these colors, we get another partition. But what you notice is that this partition is the same as the previous partition. The colors are different, but the nodes that are in each subset are the same. We have EF, EF, BD, BD, AC, and AC. And that is how we know that our algorithm has terminated and converged. G1 and G2, if we have 2 different graphs, will pass the 1WL test if they induce the same partitions. In this case, I've relabeled this graph to have a different node ordering if we order by, say, the A, B, C, D, E, F. But these are clearly the same graph. But if you were to execute this, you would see that the partitions would have different elements in them, and that's because they have these different node identities that are arbitrarily assigned. In this case, 3 has E and F. In this case, it has A and B. It's not because the graphs are different, it's because we've just shuffled around how we've identified these nodes. But we don't actually care about these identities. What we care about is the structural information. And it turns out that it's enough to just look at the counts of how many nodes occupy each of these colors. So the fact that there's 2 in this, 2 3s, 2 4s, and 2 5s in both cases is enough to say that these 2 graphs are isomorphic. There are, however, failures of this test. Some graphs that are not isomorphic still pass the 1WL test. In this example, we have a chain of nodes. Each node has 2 neighbors. Over here we have a different graph where there's 2 components. Each node still has 2 neighbors, but these are obviously 2 different graphs. If you were to do the 1WL test, each of these nodes would get the exact same tuple. It would start with the current label and look at its 2 neighbors, and they would have the same initial label. And that would be the case here as well. There's no way to distinguish the fact that this node shares a neighbor with this node, or in other words, that there's this triangle. It is only looking at the counts. We know that 1WL is not going to be sensitive to these closed triangles and be able to distinguish between them. Where does this leave us? Well, if two graphs are isomorphic, we know that they will pass the 1WL test. However, we also know that some graphs that are not isomorphic will still pass this test. In other words, if two graphs fail the 1WL test, you can confidently say that they're not isomorphic. However, if two graphs pass the test, you can't be certain that they're actually isomorphic. It's interesting to think about GCN through the lens of it being a differentiable approximation to this algorithm. If you look at this color reassignment step, we see that it includes the current label and then the label of all of its neighbors. And with that information, it maps it to a new output. Well, GCN is very similar. Instead of just getting the color, which is this one-dimensional thing, it's getting the feature vector of each of the neighbors. And recall that self-connections are included in this too, so this initial label of the current node is also included in this sum. But the point is all of the information of the current node and its neighbors is included, and then it's mapped to an output value. All of this information here is represented by H, and then this mapping function is this sum of all of those features, the linear projection, and the nonlinearity. 1WL is effectively doing message passing iterations. And what we can learn from this is that message passing GNNs, we know that they're aggregating the neighborhood information, which is going to be less discriminative than 1WL, which is deliberately mapping every unique tuple to a unique output. To be specific, let's say we have this multiset of 1, 1, 1, which represents a connection to 3 nodes of label 1. If we apply the average aggregation function in our message passing GNN, that'll give us the same answer as 1, 1, which is just a neighborhood of 2. In other words, different neighborhoods will give us the same output, and we can't distinguish between these two things. It becomes clear that when we apply an aggregation function to this multiset, we're going to approximate a mapping, but perhaps not be able to recover it entirely. So therefore, the discriminative power of a message passing GNN is going to be less than or equal to this 1WL algorithm. There are higher order WL tests that generalize the method for assigning colors to tuples of nodes. So you can consider, for example, triplets of nodes, and that can help you identify triangles and make more powerful tests. This is an active line of research for how to recreate this with GNNs. And methods have been developed, but they're relatively expensive and so far haven't offered substantial performance benefits on the types of benchmarks we typically use for GNNs, which admittedly are often simple data sets. So maybe these will prove useful for more complicated data sets, or maybe they'll become more scalable, but right now it's an interesting theoretical work, but probably not something you have to worry about practically. Finally, we have this notion of a WL kernel, where if we do these iterations of our algorithm, you can record the number of nodes that have each label and create a vector out of that. And if you have 2 graphs, perhaps they're not isomorphic, but they're similar. And what you'll see is that they'll share many numbers along these features, but they'll differ in some ways. And by taking a dot product of these vectors, it says something about the similarity of our 2 graphs. With our previous example, we started out with 6 nodes with the same color. So this first dimension essentially represents the number of nodes in your graph. And then our next iteration, we got 4 nodes of this color and 2 nodes of that color, so we can put a 4 and a 2. And then in our final iteration, we had 2, 2, and 2. This second iteration here, the 4 and 2, tells us something about the degree distribution of our graph. We have 4 nodes of degree 2 and 2 nodes of degree 3. What you see is that as you go further along in this direction, you're getting finer and finer information about your graph. But again, this is a way of representing graphs as a big feature, and then by taking dot products with other graphs, even if they're not isomorphic, you can get a measure of similarity between them. That's it for this lecture. However, you can always dig deeper. Here's a few resources I found helpful. Will Hamilton's Graph Representation Learning book, specifically section 7.3, digs into this. It's a nice introduction. However, I needed to go a little bit deeper. I got confused on a couple finer details, and I found the formalism of this paper pretty nice. This paper is not just about this. They go much deeper into other things, but their short little presentation on this topic I found very nice. There was also a great set of references in this Medium article that you might want to check out. That's it. I hope it was instructive. See you next time.